Okay, welcome back. The next quantum algorithm we're going to talk about is Simon's algorithm. Okay, so what's the setup here? In Simon's algorithm, we're given oracle access to a function f. Now the function is going to take in bits as input, and it's also going to have output of in bits. Okay, so it's a bit different than the previous cases that we've seen where the function f only has one bit of output. Now we have in bits of output. Okay, so apart from that difference, the oracle pretty much works in the same way. Okay, so we're going to have two registers. The first register is going to hold an in-bit string. The second register will also hold an in-bit string. And what the oracle is going to do is it's going to take what's in the first register, it's going to apply f of x to that and XOR that with what's in the second register. Okay, so these are both in-bit strings. So the operation that we're doing here is a bitwise XOR. Okay, so it takes two in-bit strings and then outputs an in-bit string again. And I'll just do an example here. So how does that work? So let's say we have two Boolean strings, 0, 1, 0 and 0, 1, 1. Okay, so now if I want to do the bitwise XOR of this, I just XOR every bit. Okay, so 1 and 0 XORed is 1, 1 and 1 XORed is 0. There's no carry or anything, so here we just have 0 XOR 0, and that's 0. Okay, so that's the operation that we're doing here in the second register. Okay, and here you can see the formal definition of this bitwise XOR. The subscript I here refers to the ith bit of the in-bit string. Okay, so that's the oracle. We're again going to have a promise on the function f. So this time, the promise is that there is an in-bit string s such that f has the property that f of x equals f of y if and only if either x is equal to y or x is equal to y XOR s. Okay? So again, it's similar to the previous setups where we're imposing some promise on f that gives f a certain structure. And in this case, the promise is that f of x is equal to f of y if and only if, either x equals y, of course that's always going to be imply that f of x equals f of y, or x is equal to y XOR s. Okay? So what this means is that for every bit string z in the range of f, there are going to be exactly two strings that f maps to z. Okay? So again, this is a very strong promise on the structure of f. And our goal in Simon's problem is to determine what s is. Okay, so we want to find this hidden string s. Okay, so again, we're given oracle access to f. We're promised that f has this structure determined by an in-bit string s, and our goal is to find out what s is by making queries to f. Okay, so let's see an example. So here we're working with 3-bit strings. Okay, so f maps 3-bit strings to 3-bit strings. And just to kind of give a more visual representation of f, instead of thinking of the range as bit strings, I'm just representing them as colors. Okay? So let's say that s is the string 0, 1, 1. So that means that f of x and f of x XOR 0, 1, 1, which is just 0, 1, 1 again, they both have to map to the same color. Okay? And no other input can map to the color red. Okay, so we see that no other input maps to red. Let's just take another example. Let's look at 1, 0, 0. So f maps that to green. That means that also 1, 0, 0 XOR 0, 1, 1, which is just the string 1, 1, 1, also has to map to green. Okay, and again, no other 3-bit string besides these two can map to green. Okay, so we see that indeed holds. Okay, so again, what is the setup? We have this function f here that satisfies our promise, and we can ask queries of the form, what is f of 0, 1, 1, and it'll say red. And then we can say, what is f of 1, 0, 0, and it'll say green. Okay, and we want to keep making these queries and then until we can actually determine what that s is 0, 1, 1. Okay, and the question is, how many such queries do we need to make? Let's actually start out with the classical case to get a feel for this problem. Okay, so how could you go about solving this problem classically? Okay, I'll go ahead and let you can pause the video and think about that for a minute. Okay, I'll keep going, talking about how we might solve this problem. Okay, so the first observation is, if you find an x which is not equal to y, and such that f of x equals f of y, then you're done. Okay, then you know what s is. Because then s has to be x XOR y. Okay, because if f of x equals f of y, then according to the promise, either x equals y, and we're assuming here that that's not the case, or x is equal to y XOR s. Okay, and so if x is equal to y XOR s, okay, well then if I just XOR both sides of this equation with y, okay, then the y XOR y is just the all zero string. So I'm just left with s here. Okay, so basically we can reduce the problem to this, right? Just trying to find an x not equal to y with f of x equals f of y. Okay, so get the cursor back. So if we think in terms of randomized algorithms, then this already suggests a randomized algorithm. We basically just randomly choose some set s of strings. Okay, so here's a possible randomized algorithm. Okay. Okay, so we just randomly choose a subset S of 0, 1 to the n, and then we query f of x for each x in S. Okay, so here's a possible algorithm, and then of course our hope is that there's some x and y in S such that f of x equals f of y. And then, by this argument, then we're done. Okay, so to evaluate this algorithm, the question just becomes, how large a set S do we need to choose such that with reasonable probability, there's going to exist some x and y which are not equal in S with, so x is not equal to y, of course, and f of x equals f of y. Okay, and you can show that with constant probability, this is going to hold. So we're going to have this property that there exists an x and y in S that are not equal and such that f of x equals f of y. That's going to hold with constant probability if we take the size of S to be something like 2 to the n over 2, okay? Or roughly square root the size of the whole domain, right? Square root of 2 to the n. Okay, and this is part of a a more general argument that's often referred to as the birthday problem. So basically what the birthday problem says is the kind of surprising fact that if you just take a random subset of 23 people, then with probability greater than 50%, there's going to be 2 people in this subset that have the same birthday. Okay, and it's just a probabilistic calculation, but that result often surprises people. Okay, and the kind of the generalization of that is that if you have a uniform distribution over n items, so like in the birthday problem, well, for this we assume that a person's birthday is uniformly distributed among the 365 days of the year. So if instead, we have a population where each member of the population is assigned some property with probability uniform over a set of n things, then we expect that if we just take a random subset of root n many people, then 2 of them will have the same property. Okay. All right, so that is a randomized algorithm. It turns out that in this case, you don't even have to use a randomized algorithm to achieve this complexity. You can also achieve this complexity with a deterministic algorithm. Oh yes, I should also mention that this is a tight upper bound up to constant. So you can also show that any randomized algorithm must query the oracle at least 2 to the n over 2 many times. Okay. But there's a very cute deterministic algorithm that achieves the same complexity. Okay, and this is part of a more general algorithmic framework, which is called the baby step, giant step framework. Okay, so here's how it works. First of all, you just query f of x for all bit strings x that have the most significant n over 2 bits set to 0. Okay, so again, there's like 2 to the n over 2 many such strings, so you just query all of these strings. Okay, then you query f of x for all x with the n over 2 least significant bits set to 0. Okay, so again, this is like 2 to the n over 2 mini queries. Okay, and now once you've queried all these strings, you're actually guaranteed to find a collision. Okay, so let's think about why that is. Yeah, so overall we make 2 times 2 to the n over 2 many queries there. So now think about the secret S, right? We are promised that there is such a secret, such that f of x equals f of y if and only if x equals y or x equals y XOR s. So let s be the secret. Now we must have queried the string L, which agrees with s on all the n over 2 least significant bits. And we must have also queried the function on the string h, which agrees with s on the n over 2 most significant bits. Okay? And note that L XOR h is equal to s. Okay? So since h XOR L equals s, we must have that f of h is equal to f of L. Okay, and since we also know that s is not the all zero string, then L must be different from h. Okay, so what this shows is that amongst all our queries in the baby steps and the giant steps, there must be 2 strings, h and L, that XOR to s, and therefore f of h is going to be equal to f of L. Okay? And then we can determine s. Okay, so that's a deterministic algorithm that achieves query complexity order 2 to the n over 2, and we even know a randomized lower bound of omega 2 to the n over 2. Okay, so that's the classical query complexity of this problem. Now let's look at the quantum query complexity. Okay, so the algorithm is again going to be very similar to what we saw with Deutsch-Joseph's algorithm and Bernstein-Vazirani. Okay, it's basically going to be Hadamard, query, Hadamard. Okay, things are slightly different this time because, well, first of all, we do have a function with n bits of output, not just 1 bit of output. We're just going to use the mod oracle, not the phase oracle. And after we do this quantum part, we're going to have to do some classical post-processing. Okay, but the quantum part is very similar. Hadamard, query, Hadamard. Okay, so let's go over the algorithm. So the first thing that we do is we just set up the uniform superposition on the first register. Okay, we initialize the second register with 0. Then we apply the oracle. So that gives us this superposition with the value of f in the second register. And then we're just going to apply the Hadamard on the first register again. This algorithm, we're going to do something slightly different than what we did before. So after step 2, we're going to go ahead and measure the second register. Okay, so you don't have to do that as far as the algorithm goes. You can go ahead and apply step 3 and then measure. But it just makes it slightly easier and more clear, I think, to explain what's going on if you go ahead and measure after the second step. It just saves us some writing. You don't have to deal with the superposition anymore. And I think it makes it easier to see what's going on. Okay, so before we do step 3, we're going to go ahead and measure the second register. Okay, so let's see what happens when we measure the second register. And to see what happens when we measure the second register, it's useful to rewrite the state according to the value in the second register. Okay, so remember again that f has this special property that every z in the range of f, there's exactly 2 distinct x and y which map to z. Okay, so we're going to go ahead and write the state according to these values of z. Here I've just written it as f of x. And there's going to be exactly 2 strings which map to f of x. That's going to be x and x XOR s. Okay. And since I'm summing over all x's here, so I'm actually going to have a state appear here twice, right? Because I'm going to get that state when I have x here, and also when I have x XOR s here. Okay, so that's why I have this factor of a half out front. Okay, so right, so now I've just rewritten the state like this, and now it's easy to see what happens when we measure the second register. We're just going to see some random value z in the second register, and then superposition of x and x XOR s, which both map to z under f. Okay, so that's what I've done here. Okay, so now you see the outcome after measuring is something like this. And now we're going to go ahead and do step 3 and apply the Hadamard to the state. Okay, good. So now let's see what happens when we apply the Hadamard to the state. Okay, so here I've just written out what we know the Hadamard does to a basis vector. Okay, so the Hadamard acting on x is just going to be a sum over all y minus 1 to the x dot y, and to the state x XOR s here, well, it's just the same thing. It's and now in the exponent here I have x XOR s dot y. Okay, and now I'm going to use a distributive identity here. Okay, so you can just easily check that x XOR y, s dot product with y, mod 2 is just x dot y plus s dot y mod 2. Okay, so I'm just going to use that identity here. Okay. So I haven't done it yet. I've just grouped things by y there. And now I'm going to apply this identity here. Okay. So this expands to x dot y plus s dot y. So now I have a minus 1 to the x dot y, both in the first term and the second term. So I just factor that out. And this is like 1 plus minus 1 to the s dot y. Okay, good. So now let's think about this term for a second, this state for a second. Okay, and now my question becomes, for which y does this state have non-zero amplitude? Okay, So you notice that if s dot y is 1, then this is going to evaluate to -1, and it cancels with the +1 here. So I'm not going to get any amplitude on that y. Okay? So that means that this state only has non-zero amplitude on those y for which s dot y is equal to 0 mod 2. Okay, so that means that when we measure this state, we're just going to get a random y with the property that s dot y equals 0 mod 2. Okay? So you see now that that's giving us some information about what s is, right? And we kind of think that that's giving us about one bit of information about what s is. And if we just repeat this process n many times, then we can learn s. Okay, in fact, that's the case, but it does require a little bit of argument. So I'm going to go through that argument now. So let y sub s be the set of all y's such that s dot y equals 0 mod 2. Again, when we measure this state, we're just going to get a random element of ys. Okay, now we're just going to repeat this whole quantum algorithm k times. Okay, so again, we just start from scratch, do the algorithm, measure, we get some string y. Okay, and let's say we repeat that k times, and we get the strings y1 through yk. Okay, now I'm going to put this y1 through yk as the rows of a matrix. I'll call this matrix A. Okay, now let's just look at the linear equation ax equals 0 over mod 2. Okay, so over f2 to the n. Okay, so we have this equation ax equals 0. And now let's think about what the solutions to this equation are. Okay, so the right-hand side is 0. We have a homogeneous equation here. So x equals 0 is always going to be a solution. But x equals s is also going to be a solution, right? We know that that's going to be a solution here. Okay, that's what we saw in the previous slide. The property that no matter what string we get back from the measurement, it must satisfy that it is, no matter what string y we get back from the measurement, it must satisfy that y dot s equals 0. Okay. So depending on the value of k, of course, there could be other solutions to this equation, but the important thing is that we know that s is always going to be a solution. Okay, and basically the idea is we just want to keep repeating this until 0 and s are the only two solutions. Okay, and if those are the only two solutions, then we're able to identify s. Okay, so that's the plan. So now the question just becomes, one of linear algebra. So when is 0 and s, when are 0 and s the only two solutions to this equation? So I claim that if the rank of a over f2 to the n is n minus 1, then 0 and s are the only solutions to this equation. Okay, so why is that? Well, if the rank of a is n minus 1, and we know that these are n-dimensional vectors here, so that means that the dimension of the kernel of a, right, so the set of all things that map to 0 under a, must be 1. Okay, so here we have this one-dimensional subspace of f2 to the n, and we know that s is in that subspace. Okay, and therefore s must actually be the only vector in that subspace. Okay, so it's slightly different than maybe vector spaces over the reals that you might be more familiar with, right? In that case, if you have a one-dimensional subspace spanned by a vector v, then that subspace already has infinitely many elements, right? Because you can look at any scalar multiple of v, and the scalars are taken from the reals. So in this case, since we're working over f2 to the n, then our scalars are chosen from f2. Okay, so that means we only have two choice of scalars, 0 and 1. Okay, so the span of just the vector s is 0 times s and 1 times s. Okay, so it only contains 0 and s. Okay, so if this kernel is one-dimensional, then it just contains 0 and s, and therefore we can find s. Okay, so yeah, so that is done. So basically what we need to do is we need to repeat the algorithm the number of times k such that with constant probability the rank of this matrix becomes n minus 1. Okay, so that's our next task. Okay, we need to estimate how many times we need to repeat this process so that this matrix has rank n minus 1. Okay, so let's see how we can do that. So let's kind of think about this inductively, okay? So say that we've found vectors y1 through yl, and we know that they're linearly independent. And suppose that L is still less than n minus 1. So now let's just choose yl plus 1 randomly from this set that we know that it's coming from, right? The set of things that have 0 dot product with s. And what is the probability that yl plus 1, that we get a linearly independent set again, right? So that yl plus 1 is not in the span of y1 through yl, okay? So again, the argument is similar to what we just said. You know, it's important that we're working over f2 and not the reals. So over f2, y1 through yl span at most 2 to the l many elements, right? Because that is, you know, all the combinations of scalar multiples that we have for l many elements. Okay, so the probability that yl plus 1 is not in the span is at least the probability that yl plus 1 is not in this subset of 2 to the l many elements. Okay, and since we're choosing y at random from a set of size 2 to the n minus 1, the probability that yl plus 1 is not in this, you know, an arbitrary set of size 2 to the l is at least this, okay? And assuming that L is strictly less than n minus 1, then this is going to be at least a half, okay? So the idea is that with each step, with probability at least a half, we're going to be getting we're going to be increasing the rank of our matrix A, okay? So in other words, that means that the expected number of trials to find n minus 1 linearly independent strings is at most 2 times n. Okay, because in general, you know, an expectation will, 2 trials will increase our rank by at least 1. Okay, so that means that if we just do a constant times the expected number, so say we do 10 n many trials, then we will succeed with probability at least 4/5, okay, by Markov's inequality. Okay, we do 5 times the expected number, then the probability that we don't succeed will be at most 1/5. Okay. Okay, so now we finally have our answer. We just need to repeat this process 10 n many times, and with probability at least 4/5, we will arrive at a matrix with rank n minus 1. Then the only 2 solutions to this equation will be 0 and s. And we can find s just by classically solving this system of linear equations, say using Gaussian elimination, in time order n cubed. Okay. Okay, so let's just review what happened. Okay, so the quantum part of the algorithm is again just Hadamard query Hadamard. Okay, so this takes like 2n plus 1 gates in each round, just do the Hadamards. Again, we're assuming that we get this oracle OF for free. The number of rounds is at most 10n to achieve success probability 4/5. So the total number of quantum operations is about order n squared. Then we do this order n cubed time classical computation, solving a system of linear equations to actually find S. Okay, so overall, right, the number of queries we made is order n, the total time is order n cubed, and that compares to the omega 2 to the n over 2 classical randomized complexity. Okay, so that is a summary of the complexity of Simon's algorithm. And here's just a summary of all the quantum algorithms that we've seen so far. The first one we saw was Deutsch-Josa. So the deterministic complexity of this was near maximal, but it's very easy for both randomized and quantum algorithms. Then we saw Bernstein-Vazirani, which also achieved a separation between quantum and randomized algorithms. But in terms of the trivial complexity, which is 2 to the n, this is, usually we consider this a kind of small separation, right? Because this is like the logarithm of the trivial complexity, and this is constant. And now with Simon's algorithm, we kind of get a more satisfying separation between the randomized query complexity and the quantum query complexity. Okay, so we get something like n versus 2 to the n over 2.